Okay, so in this video, we will sketch the graph of the following function. So, of course, we will need to find the first and second derivative. So let's do so. And of course, since we're going to look for critical points and inflection points, we need to find where the first and second derivative are equal to 0 and undefined. As both are polynomials, they can never be undefined, so they can only be 0. So that means if you have a polynomial or any type of expression and you want to find its zeros, you try and of course factor the expression. So we can factor here a multiple of 3. And now we have a quadratic polynomial. We can try and factor with the product sum trick. So two numbers whose product is 3, whose sum is -4, those are of course -1 and -3. The second derivative is a lot easier to factor. We can factor as 6. And this completes the factoring. And if we can, when we sketch a graph of a function, we try and find the zeros of the function, again, if possible. So we have, again, a polynomial. We try and factor. We have an obvious common factor of x that we can factor out. And we have, again, a quadratic polynomial. So we can try and factor by inspection. If we can, of course, so we would need to find two numbers whose product is +9 and whose sum is -6. This is, of course, -3 and -3. So we have x minus 3 squared. So now we have the function fully factored, the first derivative fully factored, and the second derivative fully factored, so we're good to go. So first, the zeros of the function. Well, this is now trivial, right? As we factored the function, y is equal to 0 if x equals 0 or x equals 3. We usually try to find also the y-intercepts, right? The zeros are the x-intercepts, the values of x where the function crosses the x-axis. So let's find the y-intercept. The point at which the function crosses the y-axis. This is of course trivial. We simply evaluate y at x equals 0. And of course, when x is 0, y is also 0. And we recover the familiar 0 that we have already found. We can now look for the critical points, which I'll label as CP. And again, the first derivative is never undefined. So there are no critical points of the second type, only those of the first type when the derivative is equal to 0. But this is now again trivial as we factored fully the first derivative. This can only be 0 if x is 1 or if x is 3. So we have two critical points, x equals 1 and x equals 3. Let us now find our inflection points, or possible inflection points. Again, the second derivative is always defined, so we have no possible inflection points of type 2, only those of type 1 where the second derivative is equal to 0. And again, as we factor the second derivative, this is trivial. The second derivative is 0 if x equals 2. So we now have the zeros, the y-intercept, the critical points, and the inflection points. What we now have to do is classify those two critical points. So we have to find out what does the graph of the function look like around x equals 1 and x equals 3. And of course, to classify critical points, we will simply use the second derivative to tell us at each point whether the curve is concave up or concave down. Let me put this here. So x equals 1, x equals 3. So let's put two different x-axes. One for x equals 1, the other for x equals 3. And again, we ask, well, what does the function look like around these 2 points? Well, since those are 2 critical points where the derivative is 0, at this point the curve is flat, therefore it has a horizontal tangent line in each case. So we know that the curve at x equals 1 and x equals 3 is flat. Now is it concave up or concave down? So we now use our second derivative at each critical point. And again, we do not have to find the exact value in either case, only the sign of the expression. Will it be positive or negative? So let's plug back in our second derivative now, x equals 1. So 1 minus 2 negative 1 times 6 is negative 6. So the result is negative. At 3, 3 minus 2 is 1 times 6 is positive 6. So the result is now positive. So at x equals 1, the curve is flat and concave down. And at x equals 3, the curve is concave flat, but the curve is flat but concave up. So the graph must look like this around x equals 3. So at 1 we have a local maximum, and at 3 we have a local minimum. And now, all we really need are the table of values. So the exact y values at those interesting x values. So let's put in first the interesting x values. So 0 and 3. Now those have trivial y values as both 0 and 3 for x were zeros of the function. So y is of course 0 in each case. Then the other interesting points were the critical points. Well, x is 3 we already have. The y value is 0. So we're missing x equals 1. So let's look up. What is y equal to when x is 1? Well, plug in here for x for 1, you get 1. 1 minus 3 negative 2 squared is 4. So the corresponding y value is 4. And finally, the possible inflection point, x equals 2. So when x is 2, y will be equal to, well, 2 times 2 minus 3 negative 1 squared is 1, so simply 2. So we have now for each fundamental x values the corresponding y value. So with our table of values and the classification of our 2 critical points, we can now sketch this function fairly accurately. And again, when you sketch the graph, the axes do not have to be up to scale. As long as it looks remotely okay, it'll be fine. So we have, if you look at the range of x from 0 to 3, and y is 0 to 4, so we can go in steps of 1. So x equals 1, 2, 3, 4, negative 1, negative 2, and so on. Same for y. And now let's include our points. So we have our two zeros when x is 0 and x is 3. And then let's include now our critical points. So they were x equals 1 and x equals 3. So we already have the point 3, 0. Now we're missing the point 1, 4. And we know what the function looks like around each point. At 1, the graph looks like this. So we can now include this in our graph, flat and concave down. Then at 3, the curve is flat but concave up. And the other point, if you recall, x equals 2, was a possible inflection point. As x equals 2 was a solution to the second derivative being 0, concavity may change at x equals 2. And let's find out. So if concavity changes, it can only change at a point where the second derivative is 0 or undefined. The only solution was x equals 2. And let's see. On the left of 2, the curve is concave down, but on the right of 2, the curve is concave up. This tells us that because there is a change in concavity from concave down to concave up between 1 and 3, the change has to occur exactly at x equals 2, the only point that made the second derivative equal to 0. So we have to make sure that when we sketch this portion, it's clear that the curve is always concave down on the left of 2, and as soon as we hit 2 and we just get a little further away from 2 on the right, the curve switches right away to concave up. And now, well, between 0 and 1 there is nothing of interest, as 1 was our critical point that we classified, but 0 is simply a 0, so there's nothing that's going to change between 0 and 1, so the curve continues to be concave down and hits 0 at the origin. Always, always concave down. And now if you look at the picture that we have, so concave down, then at 2 becomes concave up, and we're left with now two questions. As on the right of 3, there are no other critical inflection point, the curve can never change its behavior again. As it is increasing and concave up, it will remain increasing concave up forever. And the same can be said on the left of 0. On the left of 0, we found no other critical or inflection point. So as the curve now is going this way and concave down, it will remain like this forever. So we're left with two questions. Does this function have any horizontal asymptotes? So where is y going as x goes to positive infinity? And where is y going as x goes to negative infinity? So let's find out those two limits. And if you recall, the function was x cubed minus 6x squared plus 9x. And this may seem like a tricky limit as there are three terms and they all go to infinity, but if you recall, by far the larger term is x cubed. X cubed is much larger than x squared and x when x is large. So to emphasize that x cubed is a dominant term, we simply have to factor it. And if we do, we are left with 1 minus 6 over x plus 9 over x squared. And we'll already write down the limit as x goes to now negative infinity, checking for possibly a left horizontal asymptote. And now if we check the case, we find that we have a trivial limit. As x goes to infinity, x cubed goes to infinity. And as x goes to infinity, 6 over x and 9 over x squared both go to 0, so we're left with infinity times 1. And of course the result is infinity. So as x become larger and larger and positive, so as we move towards the right, y also becomes larger and larger and positive. So y will never stop increasing and shoot up to positive infinity. So on the right we have no horizontal asymptote. And on the left, well, as x tends to negative infinity, as 3 is odd, x cubed also tends to negative infinity. 6 over x, 9 over x squared both go to 0, so this term will be approaching 1. And of course, the limit now is negative infinity. So as x moves further and further on the left, y shoots down to negative infinity. So the curve will always keep going like this forever. So we also on the left have no horizontal asymptote. And now we have a fairly accurate sketch of the function. The curve is increasing concave down. Then at 1, it reaches a local maximum, becomes decreasing concave down. At 2, we hit an inflection point, then the curve continues to decrease but becomes concave up. At 3, we hit a local minimum, then the curve goes from decreasing to increasing and remains increasing concave up forever. So we can label now these 3 key points. X equals 1 is a local maximum. X equals 3 is a local minimum. And x equals 2 is indeed an inflection point. And that's it.